Good day everyone, and welcome to the second video in a series illustrating the solution to the classical problem of doubling the cube. Now let's explore the double mean proportion, shall we? So this can be read as A is to X, as X is to Y, as Y is to B. X is to Y represents the scaling ratios in similar cubes, where A here is the volume of the larger cube and B here is the volume of the smaller cube. So we have a relationship between side lengths X and Y. Then the ratio Y over X represents how much larger the larger cube A is when compared to the smaller cube B. In scaling down, or to scale down from the larger cube A to the smaller cube B, we multiply the larger volume A by the ratio X over Y. Such ratio ensures that we can bring the size back to the original larger cube A. Conversely, to scale up from the smaller cube B to the larger cube A, we simply multiply the smaller volume B by the ratio Y over X. This process enlarges the smaller cube B to proportionally match the dimensions of the larger cube A. Using the ratio Y over X is crucial because it dictates how much larger or smaller the cubes are relative to each other. So it serves as a scaling factor that allows us to transition from different sizes while maintaining a geometric similarity between the cubes. The theorem of similar triangles was known and formulated before the Delian problem. This was established by the ancient Greeks as well. It is attributed to the mathematicians such as Thales of Miletus, Pythagoras, who lived around the 6th century BCE. On the other hand, the Delian problem, also known as the problem of doubling the cube, was a problem from ancient Greek mathematicians that arose from the 5th century BCE. It involves finding the side length of a cube that has double the volume of a given cube. So this problem was later proven to be impossible to solve using only the tools of compass and straight edge. So that is classical geometry for Greeks, which was established by the work of mathematicians such as Eudoxius and Archytas in the 4th century BCE. Similar triangles predating the Delian problem. Okay, so the understanding and the use of similar triangles predate the Delian problem or doubling the cube, as these concepts were fundamental in Euclidean geometry. Similarity principles of similar geometric objects like similar cubes, including those derived from similar triangles, are fundamental in understanding and solving various geometric problems. The idea of similar geometric objects, such as similar cubes, fits within the broader context of Greek geometric explorations. We will explore more on the double mean proportion in GeoGebra later. In the meantime, let's discuss the double mean proportion statement. So let A be the target volume of the cube. Volume A is proportional to side length X. That's why we have A is to X. Then let B be the initial volume before the doubling. Volume B is proportional to the side length Y. That's why we have Y is to B. Side lengths X and Y are proportional. Again, doubling the volume does not mean doubling the sides. That's why we need to find X and Y in this equation. Now let's set up a system of two quadratic equations. So we use the double mean proportion to derive quadratic equations. So we start with x over y is equal to y over b. After cross multiplication, we now have y squared is equal to xb. Next, we have this equation. We have a over x is equal to y over b. After cross multiplying, we have xy is equal to ab. So this is our second equation. So you might be wondering how the ancient Greeks solved the double mean proportion. So here are some of the historical accounts given by ChatGPT. Please validate these accounts by reviewing related literature. Such a thorough research is out of scope in this video lesson. So please pause the video for these historical notes. It's worth mentioning and studying the works and collective effort and contributions of Menaechmus, Eudoxus, Diophantus, and Aquarisme for this problem, doubling the cube. So let's now solve for x and y in the system of quadratic equations of the Delian problem. So first we solve for y in equation 1. The first quadratic equation is y squared is equal to xb. So we take the square root of both sides. So we now have y is equal to square root of xb. Next, we're going to substitute the value of y into equation 2. xy is equal to ab. The second equation again. So we substitute the y with square root of xb or square root of bx. So we have x times square root of bx is equal to ab. So we copy the right side. Next, we rewrite this equation this way. So x raised to 2 over 2 times x raised to 1/2 times square root of b is equal to ab. We add the exponents of these two factors because they have a common base here, right? So we copy x and then we add the exponents. 2 over 2 plus 1/2. So add the numerators, we have 3, then copy the denominator 2. We now have x raised to 3/2. And then we're going to divide both sides by square root of b. So we now have x raised to 3/2 is equal to ab over square root of b. Next, we raise both sides by the power of 2/3 so that the exponent here at the left side will be equal to 1. 3/2 times 2/3 is equal to 1, right? So we just have x on the left side, and then we rewrite everything at the right side this way. For the radicand, we distribute the exponent 2 to a, b, and square root of b, all with the index of 2. We simplify further, so b squared over b is equal to b. So the value of x then will be cube root of a squared b. Next, we substitute the value of x, this value here, to the equation xy is equal to ab, this equation number 2. So we replace the letter x here with this expression, cube root of a squared b. Then copy y, so we have times y equals ab. And we divide both sides by the cube root of a squared b. So we now have y is equal to ab over cube root of a squared b. So we have the value of x and we have the value of y. Derive the ratio. Compare the value of x and y. So we have the ratio cube root of a squared over b over ab over cube root of a squared b. So we perform division by multiplying the numerator by the reciprocal of the denominator. So we now have this numerator here, cube root of a squared b squared, and the denominator is ab. So we have the exponent 2 here. We distribute it inside. So we have a squared squared. So 2 times 2 is 4. And then b squared is b squared. So our numerator now is cube root of a to the fourth b squared. So we divide the factors. So we can rewrite the radical expression here this way in order to have all exponents without the radical sign. So we just have rational exponents, right? So we have a raised to 4/3 minus 3/3. So we just have a to the raised to 1/3. And then b raised to 2/3 divided by b raised to 3/3. So we have b negative 1/3. So we can have that as the denominator. So we have a raised to 1/3 over b raised to 1/3. And the reciprocal of this ratio is b raised to 1/3 over a raised to 1/3. In other words, in the double mean proportion, ax equal to x over y equal to y over b, our geometric means are x is equal to cube root of a and y is equal to cube root of b. In order for a and b to have a geometric relationship to be used for the scaling up and scaling down of the two cubes with volumes a and b.